Friends, so this के क्रॉस भी आपको So hello friends, I welcome you all on this YouTube channel. So this question has been asked in ESE 2001. Let us solve this question. Please read the question statement. The Norton's equivalent of the circuit shown in the figure 1 is drawn in the circuit shown in the figure 2. Then find the ISC and R equivalent, right? ISC is the short circuit current across the terminal 1 and 2. And R equivalent is the equivalent resistance when seen from the terminal 1 and 2, right? So out of these four options, A, B, C, D, only one option is correct and you have to choose that correct option after solving, right? So I have explained that first of all, in order to solve this Thevenin's and Norton's questions, first of all, you should remove the load resistance which is connected across the desired terminal across which you want to find out the Thevenin's and Norton equivalent circuit, right? So you know that in Norton's equivalent circuit, it is the parallel combination of Norton current I Norton, which is nothing but the short circuit current across the desired terminal, and R equivalent is the R Norton, Norton's resistance across the terminals, across the desired terminals, right? So when you connect these two, that means I Norton, which is nothing but the short circuit current, and R Norton in parallel, then you will get the Norton's equivalent circuit. The same circuit you can see here, right? So short circuit current is the nothing but Norton's current and R equivalent is the Norton's resistance, right? So in order to calculate the short circuit current, first of all, short circuit the terminals across which you want to find out the Norton's equivalent, right? So how to solve this question? See here, this is the circuit. 2-volt voltage source is connected here. In series with this, you will see a 3 ohm resistance. This is a 2 ohm resistance, and here it's a resistance of 4 by 5 ohms, right? And the terminals across which you want to find out the Norton's equivalent are terminal 1 and terminal 2, right? So these terminals will be indicated to you, right? Across the given terminal you will find out the Norton's equivalent, right? So in this question, first of all, step number 1 is you should first remove the load resistance which is connected across the desired terminals across which you want to find out the Norton's equivalent. So these terminals are, you will see that no any load resistance is connected already. It is disconnected, it has been disconnected already, so no need to remove anything, right, across the terminals 1 and 2. So now you just make these terminals short circuit, right, in order to find out the short circuit current. ISC, suffix SC indicate that this is a short circuit current, right? SC indicates short circuit. So this short circuit current is nothing but the Norton's current, right? The short circuit current is nothing but this is called Norton's current, I suffix N, Norton's current, right? So now your first step is to find out this short circuit current, right? So just you will apply either KVL or KCL, right? Whichever is easier, you should choose that. So I am going to choose Kirchhoff's current law because it is easier in this question, right? So here this terminal, this is at ground potential, this is, you will see that this is at the ground potential. That means potential of this node is 0 volt. Potential of this node is 0 volt. This is at ground potential, right? So with respect to this 0 volt, what is the potential of this node? See, this node and this node both are one and the same, right? Simply he is connected these two nodes by a wire. So that means potential of this node is nothing but 0 volt, right? So this is also 0 volt. Similarly, this is also 0 volt. So this is a 0 volt, right? This is 0 volt. Now you have shorted terminal 2 with terminal 1. That means both 1 and 2 are shorted. Both the terminals are shorted. That means this voltage, that means voltage of this node, potential of this node 1 will again, it will be 0, right? Because both are shorted by a wire, right? You have shorted this. That's the process by which you calculate the Norton's current, right? So here this potential of this node is nothing but 0 volt, right? This is 0 volt. Now this is 0 volt, this is 0 volt. So across this branch, what will you find? Will you find voltage or will you find current? This is also 0 volt, this is also 0 volt. That means potential difference is 0, right? So definitely voltage you cannot find. So what can we find? Answer is current, right? So across the short circuit terminals, you cannot find the voltage. That means you will only find the current, right? Across the shorted terminals. So that's why I'm going to find, that's why we will find the short circuit current, which is nothing but the Norton's current. Just recall the Thevenin's equivalent circuit, the process of Thevenin's. When we calculate the Thevenin's equivalent, then we first calculate the Thevenin's voltage across the desired terminals. Then after removing the load resistance across the desired terminal, the terminals become open circuit, right? Now across those open circuit terminals, what can be found? You can only find voltage across the open circuit terminals. You cannot find the current. So that's why in the Thevenin's question, in the Thevenin's numerical, across the desired terminals, you will find the Thevenin's voltage, which is nothing but the open circuit voltage, right? But in Norton's equivalent circuit, for the calculation of Norton equivalent circuit, across the desired terminals, the process is that first of all you will remove the load resistance, and then after you will short these terminals. So once you short these terminals, you can only get the current, right? So that's why you will now find the current, which is short circuit current. This is nothing but the Norton's current. You cannot find the voltage across this branch, right? Because it is 0 only, because shorted, right? So that's why you find the current. So this current is nothing but the Norton's current. Now this is 0 volt. So can you tell me, if the potential of this node is 0 volt, can you tell me potential of this node? Right, now you cannot tell because you do not know the voltage drop across this resistance or across this, right? Voltage drop across these resistances are not known. So at the initial stage, it is good enough to assume that potential of this node is V0, right? Assume some potential of this node. Let me assume that this is V0. Potential of this node, this middle node, is V0. Now if this is 0 volt, what is the potential of this node? What is potential of this node? If this is a 0 volt, then potential of this node will definitely be higher by 2 volt, right? Because it is plus sign, right? Upper side you will see a plus sign. So potential of this node is plus 2 volt, right? So that means potential of this node is 2 volt higher with respect to this ground potential, right? That's the meaning of this polarity, right? Now I am going to apply Kirchhoff's current law at the node. So apply Kirchhoff's current law, right? I am going to apply Kirchhoff's current law at this node, at this middle node. So now you can write KCL, Kirchhoff's current law, at this node. So suppose the distribution of the current are like this. Suppose this current is entering like this here at this node, and this is the current which is outgoing from this node, and this is the current which is short circuit current, right? So when you apply Kirchhoff's current law at this node, you will write, so how you will write, potential of this node is 2 volt, so write 2. So if you want to find out this current, then you will write this potential minus this potential. You are assuming the current direction like this, then definitely you are assuming that potential of this node is higher with respect to this potential, then only the current will flow in this direction. If you assume the opposite direction, that means the polarities are reversed, right? All the assumption will be reversed then, right? So I am assuming the direction of current like this, that means I am assuming that potential of this node is higher with respect to this potential. So how to find out this current which is flowing like this, right? So 2 minus V naught, this is the voltage difference, divide by the resistance in between, which is 3 ohm. So 2 minus, you will write 2 minus V naught divided by 3, right? This is the current which is flowing in this branch. Now what is this current which is flowing in this branch? So this current is, so what is Kirchhoff's current law? Sum of all the incoming current is equal to sum of all the outgoing current. Algebraic sum of all the incoming current is equal to algebraic sum of all the outgoing currents. So this current will be V naught, potential of this node is 0, so V naught minus 0 by 2 ohms. So V naught minus 0 by 2 ohms, simply Ohm's law. Current I is equal to V by R, right? The same I am going to use, right? Now what is this current? What is the value of this current? Can you tell me? This current will be V naught minus 0 by 4 by 5, right? So V naught minus 0 divided by 4 by 5, right? So now you have written all the currents across this node. So now you can solve this. V naught divided by 2 plus 5 V naught divided by 4, right? So here you can further simplify this. You will write here, you take LCM 4, you will write 2 V naught, right? 2 V naught plus 5 V naught divided by 4, right? And this is equal to 2 minus V naught divided by 3, right? So this becomes 2 V naught plus 5 V naught, 2 plus 5, 7 V naught, right? So can I write this 7 V naught? So I am going to write this as 7 V naught, 7 V naught by 4, and this is equal to 2 minus V naught divided by 3, right? So when you solve this, you will get V naught is equal to 8 by 25, right? V naught, when you solve this, you will get V naught is equal to 8 by 25. You will get this, right? You have calculated this V naught now, right? Now you can easily calculate. Once you get this V naught, you can easily calculate the short circuit current, because short circuit current is nothing but potential difference of this node and this node divided by this resistance. So the short circuit current, which is nothing but the Norton current only, is equal to V naught, right? V naught minus 0 divided by 4 by 5, right? 4 by 5, So now you have calculated the short circuit current. V naught is 8 by 25, so this is 8 by 25 whole divided by 4 by 5, or you can easily write it 8 into 5 divided by 4 into 25. So when you solve this, you will get 2 by 5, right? 40 by 100, or you can write 2 by 5, right? 2 by 5, or simply 0.4 ampere, right? 0.4 ampere. So this is the Norton current, which is basically a short circuit current across the desired terminals, right? Now, how to calculate the Norton's resistance? Step number 2 is calculation of Norton's resistance. So Norton resistance is nothing but the equivalent resistance R equivalent across the desired terminal, and desired terminals in this case are terminal 1 and 2, right? Across 1 and 2, across terminal 1 and 2, right? So how to calculate? So I told you that the calculation of R Thevenin is exactly equal to calculation of R Norton, right? Norton resistance calculation is exactly same as the calculation of Thevenin's resistance, right? So basically both are calculated by the same process. And what is the process? Process is that you will deactivate all the independent sources, right? You will deactivate all the independent sources, right? So if it is independent voltage source, then to deactivate it, you will make it short circuit, and if it is independent current source, then you will make it open circuit to deactivate it, right? So to nullify the effect of independent sources, you have to do this, right? If it is independent voltage source, then you short it. If it is independent current source, then you make it open. So here see, it is a voltage source, and that too independent because its value is fixed, it's equal to 2 volt. So that definitely you will make it short circuit in order to calculate the Thevenin's or Norton's resistance, which are basically one and the same. R Norton equal to R Thevenin. So here you will make it short circuit to deactivate it. See here, I have shorted this. So simply short these two terminals, right? So once you short it, effect of this voltage source will be nullified, right? So that means effect of this voltage source is nullified, right? Now, so across these two terminals you want to find out the Norton's resistance, right? So that means you will stand here, right? You will stand here across these two terminals like this. You stand here and look towards the network, right? So that means you should stand across those terminals where you want to find out the Norton's or Thevenin's resistance and look towards the network like this, right? And then you start finding out the Thevenin's or Norton's resistance, right? So if you stand here across the desired terminals across which you have to find out the Norton's or Thevenin's equivalent, and you look across the terminals like this, right? So that means you will then realize then this 3 ohm is in parallel with this 2 ohm, right? Because they are connected in parallel. So this point, between this point and this point, 2 ohm resistance is connected, and between this point and this point 3 ohm resistance is connected, right? Because this point is nothing but this point and this point is nothing but this point, right? So 3 ohm and 2 ohm are in parallel. So parallel combination of 3 ohm and 2 ohm is nothing but 3 into 2 divided by 3 plus 2. Now the equivalent resistance of 3 ohm and 2 ohm is now in series with this 4 by 5 ohm, right? So that means I will add this 4 by 5 here, right? And when you solve this, you will find that your Norton's resistance is equal to 2 ohms. So that is the Norton's resistance, or basically equivalent resistance across the desired terminals across which you find out the Norton's equivalent, right? So which option is correct? You understand now which option is correct? Option B is correct, right? Option B is correct. So short circuit current, which is nothing but Norton's current, is 2 by 5 amperes, and Norton's resistance, which is nothing but the equivalent resistance across the desired terminals, is 2 ohms, right? It is equal to 2 ohms. So option B is correct, right? B option is correct. Option B is correct. So you understand the process now? So here remember that you should calculate the Thevenin's or Norton's resistance across those terminals where it is desired, right? So it is better that you stand across the desired terminals in order to find out the Norton's or Thevenin's resistance, right? Now one thing I want to tell you, that if you start calculating the Norton's resistance when you stand here, then the calculation of Norton's resistance will be definitely different, and that's why you will get the different answer then. If you look the terminals, if you look the network like this, when you stand here, if you stand here like this, which is wrong way. So if you stand here and look into the network like this, then the calculations of R Norton will be different, and you will get the different answer, which is wrong, because you have to calculate the Norton's or Thevenin's resistance across those terminals where you are asked to find out, right? So the desired terminals are 1 and 2, and not this and this terminal, right? So that's why the position where you are standing is very, very important in order to calculate R Norton or R Thevenin. So you cannot stand here in order to calculate R Thevenin or R Norton. You should only stand across those terminals where you want to find out the Thevenin's or Norton's resistance. And here in this question, the desired terminals are 1 and 2. He will give you this, right? He will give you that across which terminal you want to find out the Norton's or Thevenin's equivalent. He will give you. It will be given in the question, right? So that's a point which you should remember. Alright? So basically, if you stand here, which is wrong, if you stand here and calculate the R Norton and R Thevenin, then you will realize that this resistance and this resistance are now in parallel, and the combination of this resistance and this resistance is now added in series with this 3 ohm. So the calculation would then be different, and then you will get different answer of R Norton. So that will be wrong, right? So you should stand here across the desired terminal, and the desired terminals are 1 and 2 here, right? So you now get your answer, R equivalent, which is nothing but R Norton across the desired terminal, which is equal to 2 ohm, and I short circuit, which is nothing but the Norton's current, is equal to 2 by 5 or 0.4 amperes. So option B is correct, right? So unlike your Thevenin's question, in Norton question, in the Norton questions, you will see that Norton's equivalent circuit is a parallel combination of Norton's current I Norton with the Norton equivalent resistance R Norton, right? While in case of Thevenin's question, Thevenin equivalent circuit, you will see that the Thevenin's voltage source is in series with the Thevenin's resistance R Thevenin, right? So Thevenin's equivalent circuit is VTH in series with RTH. But in Norton equivalent circuit, I Norton is connected in parallel with the R Norton, right? So if you want to calculate the Thevenin's equivalent circuit, then you first of all see that which are the desired terminals across which you have to find out the Thevenin's equivalent circuit. So once you get the desired terminal, once you know the desired terminals, you will now see that is there any resistance which is connected across these two terminals. If it is connected, then you first remove it, and across these two terminals, that means it is now open because you have removed, right, the resistance. If it is connected, then you remove it. If it is already connected, then no need to remove. So if you remove this, then you will see that terminal is now open. Now across these open circuit terminals, you will now find out, you can only find out the voltage, right, because you cannot find out the current across open circuit terminals. So this open circuit voltage that you will find out, it is nothing but the Thevenin's voltage. So Thevenin's voltage is nothing but the open circuit voltage across the desired terminals, right? So this is the first step of the calculation of Thevenin's voltage, right? Next step is calculation of Thevenin's resistance. So across the desired terminals, you should find out the Thevenin's resistance. That means you should stand across the desired terminals and look into the network, and like this you will find out the Thevenin's resistance. And before finding out Thevenin's resistance, you must deactivate the independent sources. If any independent voltage source is present, then you must short it in order to deactivate this independent voltage source. And if it is independent current source is there, then you must make it open circuit in order to deactivate this independent current source, right? So under this deactivated condition, when all the independent sources are deactivated, you will find out the Thevenin's resistance, right? If any dependent source is there, then you should not touch any dependent source. They will remain as it is in the circuit, and there the calculation is different for R Thevenin. So now this is the second step for the calculation of R Thevenin. And in the third step, once you calculate V Thevenin and R Thevenin, you will connect it in series. That means V Thevenin in series with R Thevenin. So once you connect these two in series, you will get the Thevenin's equivalent circuit across the desired terminals, right? Now in the Norton equivalent circuit, the process is slightly different. First step is same. That means if you want to find out the Norton equivalent circuit, the very first step is you will remove the load resistance across the desired terminals if it is connected. And once you remove the load resistance, then the terminal become open circuit. Now the process is, according to process, you have to make it short for the Norton current, right? So once you short these terminals, you can only find out current, you cannot find out voltage, right? So once the terminals are shorted, you will find out the short circuit current, and this short circuit current is nothing but the Norton current, right? Once you find out this Norton current by KVL and KCL, right, which is nothing but the short circuit current, your next step is calculation of R Norton, right? So R Norton will be calculated exactly the same way you calculate the R Thevenin, right? That means for the calculation of R Norton, you will first deactivate all the independent sources, right? If it is independent voltage source, then you must make it short circuit. If it is independent current source, you must make it open circuit. So under this deactivated condition, you will find out this Norton's resistance. And once you find out Norton current and Norton resistance, then you will connect these two in parallel, right? I Norton in parallel with R Norton is Norton equivalent circuit, right? This circuit, right? So this is the Norton equivalent circuit that you can see from here, right? So that's the process by which you can calculate your Norton or Thevenin equivalent, right? So for all such kind of question, you can subscribe to this channel, right? So thank you very much. Thanks for watching.